All right, so these problems are the kind of problems you'll see all over the final exam, and you will see next semester and the following semester. You are going to see these until like deep into your second year. So you may as well learn how to do them correctly now. So the questions are always something like the student achieves neutrality with some particular lenses, and then the chief comes in and changes something, and then they get their final RX. So what I want you to keep in mind is that there's two main ways that they do these problems. The student finds particular prescription, and then the chief comes in and sees neutral at a particular distance. Okay, I'm not going to explain what we do yet. We'll do it as we go. And then another situation is when the student finds particular lenses, and then the chief sees against or with motion and changes something. Okay, so this is, I think, the first one. So the student achieves neutrality with minus 175, minus 150, axis 75, working at 67 centimeters. Okay, I know you might be quick to take the working distance out, but I want you to not worry about the working distance until the very end. Okay, so usually we don't take out the student's working distance. We're usually focused on the chief's working distance. So always take working distance out at the end and take out the working distance of the last person who did red. Okay, so sometimes the chief will keep the same working distance. In this case, let's start off by putting this on the optical cross. So minus 175, minus 150, axis 75. So this is axis 75. That's where the minus 175 goes. The minus 150 is the sill. So the difference, so that's minus 325 at the other axis. So minus 3.25. So that's what the student found. Okay. The chief's changes are they leave the lenses in the phoropter, and they use the concave mirror and find neutral. Okay, so they're using the concave mirror and they find neutral, which means there is no difference whether they use the plano mirror or the concave mirror. If they see neutral, it's the same thing. So I'm just going to ignore that whole part. Okay, and finds with the streak oriented parallel to the 75th meridian, they achieve neutrality at 80 centimeters. Okay, so if they're parallel to 75, they are scoping the axis 90 degrees away. So they're scoping 165. So that means all the changes are going to apply to the 165th meridian. So they achieve neutrality at 80 centimeters. So I'm just going to calculate what that is. Okay, 1.25. Okay. So the way I see it is they achieve neutrality at 80 centimeters, which means they're going to take whatever working distance correlates with 80 centimeters out from that. So they're going to take out minus 1.25. Okay, with the streak oriented parallel to the 165th, which means they're scoping the 75th, they achieve neutrality at 57 centimeters, which I think, actually I can't even remember right now. I'm going to calculate it. 100 divided by 57, that's 1.75. So when they're scoping the 75th meridian, they achieve neutrality with 57 centimeters, which means they're taking out minus 1.75. And then we just combine. So we're going to combine these two. So minus 325 plus minus 1.25. So that's minus 4.5. And then we do minus 1.75 minus 1.75. That's minus 3.5. Okay. So this one is kind of like a two-step problem. So we have the student's lenses, and then the chief keeps the lenses but changes the working distance. So we just take the working distance out, and then we're done. So we end up with this RX right here. Pay attention because the axis can flip depending on what the chief gets. So just write out what you see. So we see minus 350 at axis 75. That's the more plus between these two. So minus 350. The axis is 75. And then the difference between these two is minus 1. So that's our final RX. Okay. So for this one, a student achieves neutrality with plus 2, minus 150, working at 40 centimeters. Again, I don't care what the working distance the student was working at unless the chief doesn't change the working distance. keeping the student's lenses in place. Actually, before we get to that, let's put it on the cross. So plus 2 at axis at axis 75, and then plus 50 at axis 165. Keeping the student's lenses in place, the chief, working at 33 centimeters, uses a concave mirror retinoscope and finds that with the streak oriented parallel to the 75th, which means, so I'm just going to write it as we go. So it's parallel to the 75th, so he's scoping 165, sees 0.5 diopters of against motion. But remember, he's using the concave mirror, so I'm going to flip it as I write it. So I'm going to write 0.5 diopters of width, which is the same thing as plus 0.5. Okay? And then that's the first part. And then they have the streak oriented parallel to the 165th meridian using the plane mirror. So now this is standard. So it's parallel to the 165th. So we're scoping the 75th. And they see 0.25 width, which is the same thing as plus 0.25. Okay, so then let's put this on the cross. So we have plus 50 at the 165th meridian, so plus 50 here. And then scoping the 75th, we have plus 0.25. So plus 0.25. Let me just make sure I did that right. Okay. All right. So I'm going to erase this here. And now let's just combine. So we combine these two, and that's plus 1 here. And then we combine these two, and that's plus 2.25. Okay. Now, the first problem we did, actually, I don't want to erase that. I'll erase this. Okay, so the first problem we did, we just changed the working distance, and then we were done. In this problem, we changed the lenses, but we haven't taken the working distance out yet. Okay, so remember, the student was working at 40 centimeters, but that doesn't matter. The clinic chief was working at 33 centimeters, okay? So there's one final cross where we have to like take out the working distance. So I'm just gonna move everything around. So I'm gonna pretend this is now our gross. So what we found initially, which is this, was our gross lenses. So I'm just gonna copy this. So plus 1, and then minus 2. Sorry, that's plus 2.25. Okay, and then I'm gonna erase this. Okay, so that's the gross. And then this will be our working distance. So at 33 centimeters, that's minus 3. And he uses the same working distance for both meridians. If we combine that, so we combine this, that's minus 2. And then we combine this, and that's minus 0.75. And then the axis is still the same. And so now that we went from the student's lenses to the chief's changes, and then we take the chief's working distance out, now we have the final RX. So the final RX is minus 0.75, axis 75, and the CIL is the difference, so that's minus 1.25. Okay, so these are the two main kinds of problems you're going to see. Okay, so in one case, you have the student who sees like a particular like prescription when doing RET, and then the chief leaves those lenses in place, but finds neutral at different working distances. So in that case, you just put the student's lenses on an optical cross, you take out the chief's working distance, and that's your final prescription. Okay, and then in this situation, the student finds a particular set of lenses. The chief finds like with or against motion. So then you have to change the lenses, and then you take out the working distance. And the working distance is like whatever is the last working distance used. So whatever the chief uses. So in this case, the chief used 33 centimeters as opposed to the student's 40 centimeters. So if you can't tell from this problem, we didn't use the student's working distance at all. The only time we use the student's working distance is when the question says the chief kept the student's working distance. So with that in mind, let's move on to this problem. So this one is actually a lot simpler than the last two. A student achieves neutrality with these lenses. Let's put that on the cross. So minus 4.25 at axis 10, minus 1.75, minus 6 at axis 100. So the student, the chief leaves the student's lenses in place. So they haven't changed anything there. They see neutral at different working distances. So this is one of those cases where all we're doing is taking out a working distance and then we're done. Okay, the point of this question is to emphasize something that I mentioned before, that if you see neutral with the plane mirror or if you see neutral with the concave mirror, there is no difference. You're doing the same thing, which is just taking out the working distance. A lot of people accidentally make the working distance like a plus number. When this happens, don't do that, okay? It's still the same thing. So we're still taking a minus number out. So they see, and then the other difference with this one is that it's saying we scope the 10th meridian and we scope the 100th meridian. So all the previous questions, we've been flipping it. So we've been saying they've been oriented to the 10th meridian, which means they're scoping the 100th, right? In this case, it's very straightforward. They're scoping the 10th meridian, so what happens at the 10th meridian applies to the 10th meridian. So let's just focus on that for now. They're scoping the 10th meridian, and they see neutral at 40 centimeters. So 40 centimeters is minus 250, okay? So here's the 10th meridian. I'm going to write that here. I'll write 100 here. So minus 250 there. When scoping the 100th meridian, so that's this one right here, they see neutral at 50 centimeters, which is minus 2, using the concave mirror. But that doesn't matter because it's neutral, okay? If it was with or against, we'd flip it, but since it's neutral, it's the same thing. Okay, and so all we've done is taken the student's lenses, we've changed the working distances for both meridians, and now we just combine everything and we're done. So minus 6 and minus 2, so that would be minus 8, and then minus 4.25 and minus 250, that's minus... let me think. Minus 5.25 minus 5.75. Okay. Yeah, so then this is 10, this is 100, and so then our net lenses is minus 5.75, minus 2.25, axis 10. Okay, actually I did my math wrong, so I'm going to erase that, and then, sorry, minus 4.25 and minus 250 together, that's minus 6.75. So then our real answer is minus 6.75, minus 1.25, axis 10. Okay, and then let's move on to the last question. So a student achieves neutrality with these lenses. So I'm going to write that in. So plus 4.25, and then minus 1.75. So that's 3.25 minus plus 2.50. So he leaves the student's lenses in place. The sweet chief uses the concave mirror to find neutral motion. So concave doesn't matter here. When scoping the 10th meridian at 40 centimeters. So 10th meridian, that's over here. 100th is right there, so that's minus 250. And then when scoping the 100th meridian, they see neutral at 50 centimeters, so that's, minus 2. We just combine, so that's plus 0.50. And then we combine these, and that's plus 2.2, plus 1.75. And then so we have our final answer, plus 1.75. Minus 1.25, axis 10. Okay, that's right there. Okay. I am confident that if you understand everything I did over these 3 videos, you will be fine on RET problems, okay? But keep doing RET problems until it becomes second nature. And like on the exams, RET problems should be easy points. There's a lot of tricky conceptual questions that Dr. Nyman can ask, but RET problems only get as complicated as maybe problem number 10. I think that's as complicated as one of these problems can get. So if you understand what I did over these 3 videos, you will be fine for RET problems, okay? And if not, just email me.